Hi, this is Mr. Barron. I'm going to be showing you how to do naming for chemicals. Particularly, we're going to be learning how to name salts. We're not going to get into organic compounds until a bit later. So everything we're going to be naming today, we're going to refer to as a nomenclature system. So nomenclature, nomen means naming, and clature means system. And we're going to start off with the most simple type of naming, which is type 1 binary. Binary means, of course, there are only two elements we're dealing with. And type 1 just means it's the beginning type of naming system. So these rules are a lot like learning a language. There are no adjustments to these rules beyond what I'm giving you. So the rules we're dealing with are strictly for binary compounds, and rule number 1 is one you're probably familiar with, which is that when you write the name for a compound, you always write the cation first. Of course, a cation is what's positively charged. And then you write the anion second. And of course, an anion is negatively charged. So an example would be if I have a compound that's sodium and fluorine bonding together to form the salt, sodium fluoride, I would write the name or the formula NaF because the sodium has a positive charge and the fluorine has a negative charge, not FNA. That's totally wrong, completely wrong. Always make sure you write both the formula and the name with the positively charged ion first and the negative one second. That's rule number 1. Rule number 2. This one's a bit simple. It's simply that when you're using the name, and I've already showed you up here, that the positive one, you just leave the name exactly the same, which is sodium. And then the second one, the anion, you change the name fluorine to fluoride. So we're going to say that the cation name is just the root. So for sodium, the root would have been, well, the root is sodium. The anion starts with root and ends in IDE. So let's do an example of this one. Say I have a compound of calcium and chlorine ions. Of course, I'm going to call them chloride because it's negative. So calcium has a positive 2 charge. Chloride has a negative 1 charge. So if I want to name this compound, it would be calcium because this is the root. It's the positively charged one. Don't change its name. And then the negative one, I have to change not to chlorine, but to chloride. It starts in chlorine and goes to chloride. All right, now rule number 3. Now we're going to deal with those polyatomic ions we've learned about, which are those many atom ions. So for a polyatomic ion, the rule is that the names don't change. So I'll give you an example of this. Say you have a compound that's Na2CO3. Well, Na, of course, is sodium. CO3 we should recognize as a polyatomic ion. Its name is carbonate. I'm not going to change it to carbonatide. It's just going to stay carbonate. And those are the only 3 rules that we're going to be working with in this podcast. So just to review, cations first, anions second. The first name, you don't change. The second name, you change to end in "ide." If it is a polyatomic ion as the anion, you leave its name the same. And a lot of them often end in things like "ate" or "ite." Okay, let's go through a couple of example problems. Doing the example problems, we're going to begin with translating from the name to the formula. So say I have sodium iodide. If I have sodium iodide and I need to translate this name into a formula, it would go from Na and I, and I have to figure out the ratio that these bond, just like we did with ionic bonds. So sodium, let's find sodium on the periodic table. Sodium is in group 1, which is a positive 1 charge. Don't forget, group 1 is positive 1, group 2 is positive 2. In the middle, it can kind of vary, so we don't know exactly what their charges are all the time. Of course, no charge for our noble gases. We have a negative charge for everything in group 17. Group 16, negative 2. Group 15, some of them are negative 3, particularly nitrogen and phosphorus. And don't forget about the charge slide. Aluminum, zinc, and silver. Aluminum is always positive 3, zinc is always positive 2, and silver is always positive 1. Always. Alright, so let's go back to this. We know sodium's group 1, so it's a positive 1 charge. Iodine when it's an ion, is iodide and has a -1 charge. The charges balance each other out, so our formula is, of course, NaI. That's it. So this is an example of going from the name to the formula. Now let's do an example and practice for a while going from the formula to the name. Say I have something like lithium LiF, and I need to go from the formula to the name. So Li is lithium, F is fluorine, but I'm going to change it to fluoride. And that's it. So this is an example of going from the formula to the name. Now you'll notice that going from the formula to the name is a little bit easier. Why? Because you just need to know those 3 rules I gave you. Whenever we're going from the name to the formula, we have to pay attention to charge, and that's a little bit different. So let's do some consistent practice where we're just going to be practicing. Let me start on a fresh paper, where we're just going to practice going from the formula to the name. We're going to start off with the one where we don't have to pay attention to charge. All right, say I have the formula CaCl2. All right, Ca is calcium. I'm not going to change its name. The reason I'm not going to change its name, of course, let's go back to it, is that the cation name is just the root. That's rule number 2 in our nomenclature system. And then Cl is chlorine because it's the anion and not a polyatomic ion, even though there's 2 of them. We're just going to call it chloride. You have to memorize the polyatomic ions to know how they're different. All right, and that's it. That's the name that represents that formula. Notice I didn't put di in front of chloride. You don't do that for salts. We don't use prefixes when we're dealing with things that are inorganic. So I'm not going to put dichloride at all. So no matter how many of them there are for either ion, always leave it without a prefix. Now let's do another example. Let's go from Na2SO4 and try and write its name. Now when I write this one out, the first thing I notice is I see SO4. And that should look familiar to you. That's polyatomic ion. We know its name is sulfate. We have Na, that's sodium, and I'm going to leave that name exactly the same, sodium. And SO4 is sulfate. Rule 3 in my naming, let's go look at the rules. Rule 3, polyatomic ion names don't change. So, because SO4 is a polyatomic ion, I'm going to write sulfate. Now you're going to need to memorize all of your polyatomic ions so you can tell the difference between this and this. Note that most of the polyatomic ions end in ate or ite usually. Some of them don't. Some of them actually do end in I. So let's go through some of the common polyatomic ions. You have a list of polyatomic ions available to you, but just for helping us with naming today, let's go through some of the common ones that you're almost always going to see. NO3- is nitrate. We have CO3-2-, which is common, which is carbonate. We have SO4-2-, which is sulfate, which we've just seen. And earlier we had an example of, those are most of them, believe it or not. All right, let's do another example. Again, going from the formula to the name. And NH4 is actually another example of a polyatomic ion. But this is our only polyatomic ion that's positively charged. So NH4 is ammonium, so I'm going to write out its name, ammonium. And Cl is chlorine, which I'm going to change to chloride. And that's it. Done with that name. So these are examples of going from the formula to the name. You don't really have to pay attention to charge at all. And you know that the first one, always you write the name exactly the same. The second one you change to "ide," unless, in this example right here, it's a polyatomic ion. Don't change it to "ide," just leave it the polyatomic ion and its original name. Now we're going to go to an example of we're going to practice a little bit more of going from the name to the formula. When you're going from the name to the formula, you really need to pay attention to charge. If you're not paying attention to charge, you're not going to write out the correct formula, because the name doesn't give us information about how many of each ion are bonding together. I'll give you an example of this. Say we need to translate strontium chloride, and we want to change it specifically into its formula. I know strontium is Sr, and I know chloride is Cl, which comes from chlorine. Strontium is right here, which is in group 2, which means it has a positive 2 charge because, of course, it has 2 valence electrons, and its Lewis dot structure would be SR with 2 dots near it. So this is a positive 2 charge. And then for Cl, it should look very familiar to us. Cl is right here, which is in the negative 1 charge because it has 7 valence electrons, wants to gain 1. So we have a negative charge. So the trick is, the reason we have to pay attention to the charge is because sometimes we're going to have to do the crisscross rule. These two charges don't balance each other out in a 1-to-1 ratio at all. So what we're going to have to do is figure out how many of each go together to form a neutral compound. The way that is easiest often is called the crisscross rule. You take the number and you pull it down to the other side, opposite to it. So it's SR, and I'm not going to write anything because I'm just pulling down the numbers, not the charge. And of course, when I just write negative, that means it's a negative 1 charge, and we don't write 1s in chemistry. And then for the Cl, the 2 comes down, and I do have to write that down. And that makes sense. I need 2 chlorides, 2 negative charges, to balance out the positive 2 charge of the strontium. And this is the formula for that name. Let's do another example. This time we're going to translate, let's see here, sodium phosphate. Okay, I know sodium is Na. I know in the periodic table it's in group 1 right here, so it's got to have a positive 1 charge. But don't make the mistake of thinking that phosphate is P and it has a negative 3 charge. That's completely incorrect. Phosphate is on our list, or at least it should be, of common polyatomic ions that we're going to see a lot. Notice that it ends in 8, not I. That's your clue that it's a polyatomic ion. Because it has this 8 ending, if it was a monoatomic ion, it would have ended in I. So phosphate is PO4 3-. The charges don't balance each other out, so I'm going to have to do the crisscross rule. The 3 comes down here, so it's Na3. And then the 1 comes down here, but I'm not going to write the 1, so it's PO4. And that's it. I've translated that name into that formula. Let's do 2 more examples of this. But this time, I'm going to mix them up between going from name to formula and formula to name. So this time I'm going to give you BaCl2. Well, since we're given the formula, we have to translate it into the name. Ba is barium. Cl is chlorine, but because it's the second part, it's chloride. That's it. Done. Notice we didn't have to pay attention to the charge. Going from formula to name is pretty simple. Now what we're going to do is go from a name, ammonium nitrate, to the formula. This one's a bit more complex because we have to pay attention to the charge whenever we're going from name to formula. So ammonium is NH4+. I know it's a polyatomic ion. There is no ammonium on my periodic table at all. It doesn't exist anywhere on here. And same with nitrate. Nitrate is not nitrogen. They're not the same thing. Nitrate is also a polyatomic ion. Notice this time the charges actually balance out. That means I don't have to do the crisscross rule. So my formula is NH4, NO3, and that's it. Okay, now I'm going to show you one little addition when we're going from name to formula. This is one little thing that we have to sometimes do. Say I'm dealing with aluminum sulfate. Aluminum is Al, and I know aluminum is always a positive 3 charge. It's right here. Has 3 valence electrons, so it's a 3+. Sulfate, we know, is a polyatomic ion because it ends in 8. Has a negative 2 charge. I have to do my crisscross rule. 2 comes down here, the 3 comes down there. So it's Al2SO4, 3. But see, the way I wrote it out this way doesn't make any sense because there's not 43 oxygens. I want to show that there's 3 sulfates for every 2 aluminums. Make sure you put parentheses around your polyatomic ions when you change their number beyond just 1. If you have any other questions, please let me know and make sure you do the practice.